So far we have talked about probability distributions, and we have talked about how these probabilities that we compute from distributions that I claim to be realistic, how these probabilities can affect or govern the outcomes of certain experiments that are influenced by randomness. But in all the presentations so far, we have not talked about how we're actually going to make the connection between the theoretical computations and the actual reality. And in this presentation and the following ones, we're going to talk about how that connection is being made, how we can actually compute the parameters for the distributions, and how we can potentially also verify certain kinds of probabilities. And the answer as to how that connection to real life is made is actually fairly short, because we only have one tool, and that's random samples. And that tool is then being used in various computations as we're computing derived quantities, and these derived quantities are called statistics. Let's take a look at the exact definitions and go from there. So statistics will connect theory and practice, and well, what we have to figure out is what they are. And we start with the idea of a random sample. So first of all, a sample value is any value obtained from a stochastic or a random experiment. I don't think I've used the word stochastic in these presentations before. Stochastic, basically, if you look at a thesaurus, is another word for random. It just sounds a lot more scientific than random. Sample values, we will denote those things as x1, x2, and so on. And we will often assume that the ith sample value xi comes from a separate random variable x sub I. So we're not going to necessarily say that our experiment is the random variable that spits out all the sample values. We might just say that our first measurement is a random variable, our second measurement is another random variable, our third measurement is another random variable, and so on and so on. That just ultimately helps with the theory, it helps with some proofs, and the models are essentially equivalent. Okay, so what else are we talking about? Yes, okay, so the random variables x1 through xn are also called a simple random sample of size n if the following happens. The variables have to be independent, and we're going to stay with an intuitive notion of independence here. There is a precise mathematical definition for independence that you can learn in a full course on probability theory and statistics. Basically, for these short presentations here, we're going to go with the intuitive idea that basically one measurement should not influence another. If I flip a coin 2 times, then the first flip should not affect the outcome of the second flip, and vice versa. And when you have an experiment where you say you measure the frequency of a pendulum, then your first measurement shouldn't affect the second time you take a measurement of that frequency. Examples of things that are dependent are, for example, when you draw cards from a deck of cards without replacing the cards, because then the first card you draw and which first card you draw affects on what you can get on the second draw. So independent is that the measurements basically just, they don't influence each other. And the other thing then is that all of these random variables must have the same probability distribution. So if we're thinking of this in practical terms, then really what we're trying to model here is repeated measurements in a lab, which is certainly for the technical fields, even early on in the freshman and sophomore years, that's really the main concern, because that's what we do in labs. We take measurements and we take them repeatedly so that we can get a more reliable idea of what the exact value potentially is. Okay, so examples, well, for coin flips we have sample values of 0 or 1 for heads or tails, and the value xi is the value obtained in the ith coin flip, then it's either 0 or 1, right? So then, as said previously, and I'm just doing this to drive this point home, we often associate the separate random variable xi with the ith coin flip. The values obtained when we do repeated measurements are sample values of a process that measures, well, whatever you are measuring. I didn't put anything in there. It could be temperature, could be frequency, could be light intensity, anything you can measure basically. And the value xi then is the value obtained in the ith measurement, and we often then associate a separate random variable xi with the ith measurement. When you're looking at another example that we've seen, consecutive queries of the random variable rand, those are sample values of a random variable that is uniformly distributed on the interval 0, 1. The value xi is obtained in the ith query, and we often associate a separate random variable, capital X sub I, with the ith query. Okay, so sample values are the things that are accessible in the lab. So sample values give us something that connects theory to real life. And in fact, sample values are the only thing that can be used to connect theory and real life, because what else are we measuring, right? Anytime we try to understand what is happening in a process, what we do is we take a measurement. And then we digest these measurements and push them through models and things like that. But that's the only thing that really connects theory and practice, connects theory and real life. Statistics now, on the other hand, a statistic is a quantity that can be computed from sample data. So a statistic is a derived entity. And examples are, let's just take some examples that aren't necessarily useful just to drive home the point what it is. If I take a sequence of measurements and I multiply the first two measurements with each other, that's a statistic. Now, I don't know if that would ever be useful in any way, but a statistic, the definition doesn't say anything about whether it's useful or not. It's computed from the sample data. The fact that here I've also thrown away all the values after the second measurement doesn't really play a role. It is a sample statistic. The maximum of the sample values, okay, that's something that sounds a little bit more interesting. That's also a sample statistic. If I take my first sample value and subtract the expected value of the random variable, that's something I would like to do, right? Because that's the deviation from the expected value. But that's not a sample statistic, and it's not a sample statistic because the expected value typically is not known. In fact, we compute a lot of statistics to get an estimate for the expected value. And so if I already knew the expected value, why would I do a measurement, right? I would just put that expected value into my theory and move on. So then, similarly, if we now phrase that in a lab setting, the exact value of a measured quantity, first of all, we could certainly have a philosophical discussion as to whether that actually exists in scientific in continuous quantities. But that exact value of a measured quantity is not a statistic because it's typically inaccessible to measurement. Or let's also put it this way, if it was accessible, and in certain situations it is. For example, if I want to know how many red pieces of candy are in a bag, well, I would just call it and I have the exact count it, and I would have the exact value. But basically, typically the exact value of a measured quantity is not accessible because why else would I measure, right? If I already have the exact value, I don't need a measurement. I would just keep going. Okay, so now if I have n sample values, then we define the sample mean to be x bar, and that's just the name, and it's basically the average of the sample values, right? It's 1 over n times the sum of the sample values, and that is something that you most likely have already seen in science labs that you have taken, because this is what we do when we take repeated measurements. Then we compute the sample mean, and the sample mean, as people tell us in the labs, has a better chance to be closer to the actual value, to the exact value of the quantity, which in this case may well not be accessible to us, than the individual measurements themselves. And in the proofs that we're going to see in this presentation, we're already going to see why that may be the case. We also have a measurement of spread for the sample values, and so if n sample values are given, we define the sample variance to be s sub x quantity squared, sample variance of the random variable, sample standard deviation of the random variable squared, because remember the variance is the square of the standard deviation. And it's, well, it's almost what we predict, right? Because the variance is that you take the deviations from what you consider to be your center, which is your sample mean that you can measure. You square the deviations, you sum them up. Okay, in continuous situations we integrate, but integrals and sums are analogs. One is continuous, that's the integral, the other one is discrete, that's the sum. And then we average that out, and here's where we typically would expect a denominator of n, right? And actually it turns out to be a denominator of n minus 1. And we're going to see in a proof why the denominator really needs to be n minus 1 in lab situation. Okay, first of all, the square root of that thing is called the sample standard deviation. In a lab setting, the n minus 1 here can be attempted to be justified intuitively, but that just tells us that maybe 1 over n is not the right thing to do. It doesn't necessarily tell us why we divide by n minus 1. So things that I have heard in a lab and which are really not bad, they just don't give us the precise reason, is that if you had a sample of size 1, well, that has no variance, that has no scatter, because with one measurement you have nothing to compare it to. You don't know how far apart those values could spread. And so that means that the sample variance should be undefined for n equals 1, and certainly dividing by n minus 1 does that because we'd be dividing by 0. Small samples will also not capture the whole variability of a distribution. That also makes sense. If your distribution has a tail, how likely is it that 3 measurements will actually capture anything that's happening in a tail that has very low probability maybe? So that means that the sample variance should be larger than the discrete variance, if you will, where you divide by n instead of n minus 1. And by dividing by a smaller number, you get a larger number, of course. And for large values of n, so for large samples, of course, the difference between what we get when we just average these things out by dividing by n, or what we get when we divide by n minus 1, the difference between those two should go to 0, and of course 1 over n minus 1 minus 1 over n does go to 0. So that is something that, even without the admittedly complicated computations in these proofs, we could use to convince ourselves that maybe we ought to divide by n minus 1. I've always felt a little bit uncomfortable with that, and that's probably a reason why I became a mathematician. Well, we'll see what goes on in these proofs. Okay, so how do we formalize things now? Well, to formalize things, we have to go back to this idea that we have random variables. So for repeated queries of the same random variable, we perform the same measurement over and over again, we will consider independent random variables xk with the same distribution as x. So that's what I said earlier on, where we would associate a new random variable with every measurement. And that means we consider a random sample. And the random variable associated with the sample mean now is capital X bar, and it's just 1 over n times the sum of the random sample variables. And the random variable associated with the sample variance is capital S sub x quantity squared. And it's basically, again, it's the same formula, only that the individual values, which we could actually compute and which are numbers, are replaced with the corresponding random variables. And so the thing now is that with the formulas on the previous panel, we can do data analysis because we can plug numbers in and get numbers. Whereas with the formulas on this panel, where we have abstract random variables, with these things we can do theory. Okay, so now we're going to start doing some proofs. And let me say right here that because we really aren't working with these kinds of computations on a regular basis, I consider these proofs mainly background information. However, if we're going along a different strand that happened in these presentations, which is that these computations ultimately aren't bad for you because you will see computations that are similar in later courses where also somebody just gives you a definition and then a lengthy computation happens, they aren't bad to see. So, what are we trying to achieve? Well, what we're trying to achieve is we're trying to show that these random samples have something to do with the theory as well as with reality. If you take a random sample of size n from a population with mean mu, then the expected value of the sample mean is expected value of x bar being mu. So that means that this random variable here has the same, this new random variable has the same expected value as your underlying distribution, but this new random variable we can measure, right? And the idea then in probability is that ultimately things should in some way cluster around the expected value. So that means the measurements of x bar ultimately ought to tell us something about the parameter mu of the distribution, assuming that this theorem actually is correct. And so what we're going to do here is we're just going to prove the theorem. It's actually not that hard because the formula is simple. we're looking at the expected value of x bar. Well, that is the expected value of 1 over n, sum k equals 1 to n of the xk. What do we know about expected values? Well, we know that constant factors can be moved out, and we also know that expected values can be moved into sums. So this is actually 1 over n times the sum k equals 1 to n of the expected value of xk. But xk had the same distribution as x, which means e of xk is e of x. I think that's the next one here, yeah. So I'm summing k equals 1 to n e of x, and so that's just n times e of x, and now we can see 1 over n times n cancels, we end up with e of x, and e of x is mu. And so that means that the expected value of the sample mean is the mean of the underlying distribution. So that is now formally establishing that we now have something we can measure that is directly connected with a parameter of an underlying probability distribution that we previously had to postulate, which we now have a way to hopefully estimate. Okay, we also want to talk about the variance. So if we have a random sample of size n that is drawn from a population with variance sigma squared, then the expected value of the sample variance s sub x quantity squared is 1 over n minus 1 sum k equals 1 to n xk minus x bar quantity squared. That expected value is sigma squared. And this really is the formal reason as to why we have to divide by n minus 1. If we had divided by n here, the whole computation that follows would be the same, but the result would be that the expected value of this other quantity would not be sigma squared. And because we want to use these formulas to estimate what our variance is, well, this is the long and the short of what we divide by n minus 1 is this formula gives us an estimate of sigma squared, the other one gives us an estimate of something multiplied with sigma squared, and the factor is just not terribly pretty. Okay, so what's the proof? Well, here's something that we have to quote from the theory that we're not going to prove, and that is that when we have independent random variables, and remember we wanted to assume that these measurements here, these random samples, are independent of each other, then the expected value of a product of two of those things, and we will probably have to compute that because we have to multiply out that square, that's the expected value of the first times the expected value of the second. That is a fact about independent random variables that we're not going to prove here. Okay, but accepting that fact, we can now do the following computation. It's a little bit lengthy, but if you just follow all the steps, you can at least see that it's right, and you get a little bit used to working with these expected values. So you take the expected value of the sample variance, and of course that is the expected value of 1 over n minus 1 sum k equals 1 to n xk minus x bar quantity squared. Okay, well, if I look at that, the only sensible thing I can think of is, well, okay, I can pull out the 1 over n minus 1, I can pull out the sum, but after that I have to multiply out the quadratic. So let's see. Yeah, so I pull out the 1 over n minus 1, I pull out the sum, and I need to multiply out the quadratic, but I also need to remind myself here that x bar, of course, is 1 over n times the sum L equals 1 to n x sub L, so I'm using another summation index L here. And, well, I don't really want to work with fractions in here. I would much rather not have this 1 over n, so I'm going to factor a 1 over n out. That'll come out as a 1 over n squared, right? Because if I take a 1 over n out of the parentheses, that gets squared. And so what I get is 1 over n minus 1 stays with me. The 1 over n squared comes from pulling out the 1 over n. We keep the sum, we keep the expected value. Well, if I pull a 1 over n out of xk, that means I keep an n, right? Because what I have in front of the xk is just a 1, which is n times 1 over n. But I don't have a 1 over n here anymore. Okay, now I'm pretty sure I'm supposed to square this stuff. Yep, so let's see. I mean, it starts looking intimidating, but there's really nothing happening except elementary algebra. We keep the fraction out front, we keep the sum, and now nxk quantity squared, right? When we multiply this out, the first thing we do is we square things. Well, the n squared comes out, and I get the expected value of xk squared. Then I've got minus 2 times the first times the second, so I would get minus 2n, that's here, times xk times the sum of the xl, which we have here, and I already pulled the number out of the expected value, and then I have the square of this sum at the end, and that is, well, that is just the sum multiplied with itself, and I'm using two different summation indices to not have any clashes here. So all I've done in this line is I've just multiplied out the parentheses. I've used the binomial formula. What can we do now? Well, now we just want to puzzle things apart a bit more. So keep the factor out front, keep the summation. I can't really simplify much in this term, and so I keep that term. This term here is xk times the sum. Alright, so in this sum I have the term xk by itself also, so one of the terms will be xk squared, and so I have one term 2n expected value of xk squared. And then I've got the rest, which is xk times the sum where L is not equal to k, and that's exactly what this term is, right? So that means that this term and this term give us this term, and we've digested everything except what we have here. And this sum also decomposes into the sum of what you would consider the diagonal, namely when I is equal to 1 and j is equal to 1, I get x1 squared. When I is equal to 2, j is equal to 2, I get x2 squared, and so on. So that means this sum is the sum of the xi squared plus the sum ij equals 1 to n of xi xj when I is not equal to j. And again, I've pulled the expected value into the sums. Alright, so this is the expression that we had on the previous panel. And what can we do now? I think we can pull out some more summations. Yeah, because now, well, let's just take a look at it. We keep the factor out front. We keep the summation. We keep this guy because there's nothing else we can do with it. We keep this summand because there's nothing else we can do with it. What do we have here? I can pull out the summation and I get e of xk times e of xl, which is e of xk times e of xk, which is e of xk squared. And how many summands do I have? Well, I sum from 1 to n and I skip 1, so I've got n minus 1 summands. So really this summation here is nothing but n minus 1 times the same summand, which is the expected value of xk quantity squared. If I pull out the sum here, I just get n times the expected value of xi squared, and so that is just, I just pick a k, and I get that this is n times e of sum n times e of xk squared. And here I've got the same thing. If I pull out the sum, I've got e of xi times e of xj, which is e of xk quantity squared, because all these things have the same distribution and therefore the same expected value. And how many summations do I have? Well, if I sum for ij from 1 to n, I've got n squared products, right? But I skip all the ones where I is equal to j, which is that I skip n of them, so I've got n squared minus n summands. So that's how the n squared minus n comes about. Okay, and now it's algebra because I've got a bunch of e of xk's and a bunch of e of xk squareds. So I simply sort that. Keep the factor out front, keep the summation. E of xk squared occurs with an n squared, and it occurs with a minus 2n and a plus n. So minus 2n plus n gives us minus n, so that's this one here, and that takes care of all the e of xk squared. And then we also have e of xk quantity squared, and for that I have minus 2n squared plus n squared. Well, that's minus n squared, so that's minus n times n, okay. And I have plus 2n minus n, so that would be plus n, which is minus minus n, so that collects this stuff. And I've collected it in such a way because ultimately what I'd really like to have is term n times n minus 1, so I can start canceling. Because now, if we look at what we have here, again, factor out front stays the same. Well, n squared minus n is n times n minus 1, and we also have n times n minus 1 here, so I can factor that out. I get an n times n minus 1 out front. And what I keep inside the summation is the expected value of xk squared, which is x squared, which is the underlying random variable, if you will, minus e of x quantity squared, and that's the variance of x. And so that means, yeah, I just now do another cancellation here. I've got the variance of x added to itself n times, so that gives me n times the variance of x, and now we can already see that this numerator cancels that denominator, so we end up that this The expected value that we started out with actually is the variance of the underlying random variable. And that is why the sample variance is defined the way it is. It's defined the way it is because the corresponding theoretical quantity has the expected value that we want, which says that these measurements will ultimately cluster around something that is interesting. Okay, finally, the hardest proof, and well, I'm not sure. I think it's equally hard to what we just did. But we've got one more thing, and that is if a random sample of size n is taken from a population with standard deviation sigma, then the variance of the sample mean is the variance of x bar, and that's sigma squared divided by n. And so this is something that that you have also probably heard about in labs, and that is as you take repeated measurements, the variability of your averages goes down, and that is captured in this theorem because the variance, if you take n measurements, the variance is the variance of the underlying process divided by n, which means that repeated measurements will decrease the variance that you have in your average, but remember the variance is a squared quantity, so the standard deviation only declines with 1 over square root of n, which is significantly slower. Okay, in this part of the presentation, or in this presentation itself, we're just concerned with the abstract proof, so let's take a look at that. Well, we need to find the variance of x bar, which means one way to do that is to compute the expected value of x bar squared, and then subtract the expected value of x bar quantity squared from that. And so that means we just set that up, right? That's the expected value of the formula for x bar quantity squared, and the next thing to do is probably pull out the 1 over n squared and to multiply out the summation. So yeah, 1 over n comes out as a 1 over n squared because it's squared, and then it's coming out of the expected value. And the summation of the xk squareds, that's just the sum j equals 1 to n xj times the sum k equals 1 to xk. And what comes next, I think, should be familiar because we're again going to look at what happens when j is equal to k and what happens when j is not equal to k. Because, yeah, okay, first of all, we pull out the summations, right? We can pull sums out of expected values. So this is 1 over n squared, sum j equals 1 to n, sum k equals 1 to n, expected value xj, xk. And now that is 1 over n squared times the sum when j is not equal to k, expected value of xj times expected value of xk, plus the sum k equals 1 to n expected value of xk squared. And we have to split them up in such a way because xj and xk, when j is not equal to k, they're independent, which means the expected value of the product really is the product of the expected values. But xk is not independent of itself. And because a measurement is never independent of itself, we have to work with e of xk squared here, right? That in particular is not that bad because now we realize these xj's, they're supposed to all have the same distribution as whatever process we're getting stuff from, which is x. And so that means that if we keep the 1 over n squared, the first sum is just the sum j is not equal to k of e of x quantity squared. And the second sum, well, we just kept that. That's the sum k equals 1 to n of e of x squared. All right, and now, because we're summing the same thing, these just become numbers, right? This is 1 over n squared, and we're summing j and k from 1 to n, so that's n squared, but we skip the diagonal, so that's n squared minus n summands, so we get n squared minus n times e of x quantity squared, plus, and here we sum k equals 1 to n, so we've got n summands, so we've got n times e of x squared. And so now we can look at the variance of x bar, which is the expected value of x bar squared minus the expected value of x bar quantity squared. And we can just now take what we've computed on the previous panel and subtract e of x quantity squared, and now it's just a matter of multiplying things out for a while, I think. Because what do we get? We get n squared e of x quantity squared divided by n squared. That's just e of x quantity squared. Minus n over n squared e of x quantity squared, that's 1 over n e of x quantity squared, plus n over n squared e of x squared, that's 1 over n e of x squared, minus e of x quantity squared. We can see that this one and that one, sorry, the highlighting doesn't work too nicely, and that's something I haven't figured out how to fix. these two terms cancel, and so we end up with, well, what's left, this term and that term, and so that's 1 over n e of x squared minus e of x quantity squared, and that's 1 over n times the variance of x, which is sigma squared over n, and well, that finishes the proof. Okay, so that means we have established that measurement values digested in a certain way, namely in the formulas for the sample mean and for the sample variance, actually lead to random variables that have expected values and standard deviations that are interesting to us because they are related to the expected value and the standard deviation of the underlying stochastic process. And so now these are things that we can use to analyze parameters, to estimate parameters, and so on. We have seen the proofs. As I said, those aren't necessarily the main objective of these presentations, but at the same time, if you can push your mind in the direction of also understanding and at least being able to read and verify these kinds of proofs, quite a few theoretical advanced classes will look at least a little bit easier. With that, there really isn't that much we can assess here. I think I'll be asking you on the homework to determine if or if not certain things are statistics. Well, you can work that out, and I'll see you when we talk about the very deep and very important central limit theorem in the next presentation. Until then.